OCR A-Level Chemistry, Module 3. Let's go. So the first thing mentioned in this part of the spec is periodicity. So you need to know that the periodic table is arranged in order of increasing atomic number, based on vertical periods that have repeating trends in physical and chemical properties, and vertical groups that have similar chemical properties. And like I said, this is called periodicity, the repetition of patterns in both periods and groups. And the highest shell an element's electrons occupy is the same as the period that the element occupies in the table. So for example, hydrogen is period 1, and so its highest energy shell is the first one. But something like oxygen, its highest energy level is its second, and so it's in period 2. And like I said in my module 2 video, you can guess the highest energy subshell based on something's position in the table. Now, each vertical group has its own name, but the only ones you need to know are the alkali metals and the halogens and noble gases. And unlike in GCSE, where you had groups 0 to 7, now you have groups 1 through 18. Now, other than electrons, we also need to talk about other trends in the periodic table, but to do that first we've got to define what some key terms mean. First of which is the first ionization energy, which you can see the definition of here. And it is vital, both in your written definition and in your calculation, which you can see here, that you remember that this is about gaseous elements. And just like you can have first ionization energy, you can also have second, third, fourth, etc. And all you have to do is change the words in your definition to match the calculation you're doing. So second ionization energy is the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous potassium ions, in this case, to form 1 mole of gaseous potassium 2 ions. And we want to understand how it changes across the periods. So we're going to have to discuss why it would change. So the first reason is something called the atomic radius. So as atoms get bigger, or their atomic radius increases, the electrostatic attractive forces between the positive nucleus and the negative electrons get lesser. And so as atomic radius increases, attraction between the electrons and the nucleus decrease. And obviously vice versa. The next one is nuclear charge. Now, the more charge a nucleus holds, the greater the attraction is between the negative electrons and that nucleus. So the higher the nuclear charge, the greater the attraction. Now, the last is shielding. So this one's the most complicated out of all of them by far. But it's really simple once you get to understand it. But basically, because like charges repel, when you've got more than one electron shell, the outermost electron shell is going to be repelled by the one closest to the nucleus, which means the attraction between the outermost and the nucleus is going to be less, because you've got that electrostatic repulsion. Here you can see a simple example of an atom. This is a helium atom, 2 protons, 2 electrons, and then when you remove one of those electrons, you get, obviously, a helium ion. And ionization energy is just about how much energy it took to remove that electron, and so you can use it to work out what group elements are in. And there are certainly example questions of this, and just here you can see an example of a group 7, which is fluorine, and it kind of is very low and then peaks just after 7. And that's because after the 7th ionization, they're trying to ionize a new shell that is closer to the nucleus and so is experiencing more attraction. Now, across a period, ionization energy would look something like this, and as you can see there are 2 peaks at helium and at neon. And hopefully it's nice and obvious why, but in case it's not, it's because they're noble gases, so they already have a full outer shell of electrons. Neon has a higher nuclear charge, so why is its ionization energy lower than that of helium? Well, that's because it's outweighed by its increase in atomic radius and by the amount of shielding. So even though nuclear charge increases down the group, so does atomic radius and so does shielding, and this means that in general, ionization energy decreases down a group. Ionization energy actually increases across the period, and that's because the radius decreases. And the reason the radius decreases is because you've got more nuclear charge with the same amount of shielding. So as you can see here, this is across period 2. And like I said, it increases. But why are there little dips? Well, that's because of electron subshells. So in beryllium, you're trying to remove an electron from 2s2, whereas in boron, you're trying to remove it from 3d1. And so its ionization energy is slightly less than beryllium. Now we need to talk about bonding. We talked about bonding a lot last video, so definitely go check out my module 2 video if you haven't already. So metallic bonding is the electrostatic attraction between positive cations and a sea of delocalized electrons, and these form giant metallic lattices. And it's because of that strong electrostatic attraction between cations and electrons that most metals have really high melting points. They are also highly conductive. Because of the sea of delocalized electrons, it means charge can easily flow through the structure. However, because of how strong metallic bonds are, metals are not soluble and instead tend to react with certain solvents. So, last time we talked about simple covalent molecules, now we're talking about giant covalent structures, which hopefully some of you will remember from GCSE. Now, right off the bat, you've got something like diamond, which is carbon with 4 other carbons bonded to it. And so it has a really high melting point, because instead of intermolecular forces, it's got pure covalent bonds. These strong covalent bonds also make it insoluble. And because they're using all their electrons in bonding, none of them conduct electricity, except for graphite, and we'll talk about that now. And carbon can either form 4 bonds or 3, and so it can form hexagonal structures like this, where every carbon is bonded to 3 carbons rather than to 4, like in diamond. And this creates a planar structure that is held together by intermolecular forces between the layers. And this means that graphite, unlike diamond, is easily compressible, squishable, and very rubbery. So giant covalent structures are actually much stronger than giant metallic structures, and so you can look at a melting point graph across a period and it looks something like this. Now, you won't need to know the exact values for an exam, but you will need to know this kind of shape. So here is period 2, and then this is period 3, and again you'll need to know this kind of shape. So silicon is a giant covalent structure, and that's why it's at that peak. So now we need to look at group 2. Now, you don't need to know the name of group 2, but you do need to know some things about it. Now, all group 2 elements have S2 as their outermost subshell, and so because of this, they all form 2+ ions. And so all reactions with group 2 and oxygen look something like this, and likewise with an acid look like this. Now, reactivity increases down group 2, and you'll remember that's because ionization energy decreases going down group 2 as well. Now, if you have a metal oxide and you react it with water, then you get that metal ion and 2 OH- groups. And then it gives you a metal hydroxide, which is a base or an alkali if it's aqueous. In fact, as you go down group 2, the solubility of their hydroxides increases, which makes them more alkaline. Now, some of these metal hydroxides are really useful. One of them is calcium hydroxide, which is also called lime. You may have also seen it called quicklime, and it's used in agriculture to reduce acidity in soil. So in massive farming operations, things like that, where they need a specific acidity to grow whatever they're growing, they'll use quicklime if they find that their soil is too acidic. Now, you can also use these to make magnesium chloride and calcium chloride, and these are antacids, and you'd use them for things like indigestion. Moving on, we have the halogens. Now, all of the halogens are diatomic, and melting point and boiling point increases down the group, which you can see here. Now group 7 form ions through gaining electrons, which creates negative ions, and so reactivity decreases down group 7 because it works in the opposite way to ionization energy, because instead of losing electrons, you're gaining them. Now when you have a metal halide or ammonium halide, the introduction of a more reactive halogen will cause the ammonium ion or the metal ion to react with the halogen, and so the halide is displaced. And this will mean that the solution will change colour, so you can use this to test for halides. So if you add cyclohexane to iodine and bromine, they will turn different colours. Bromine will turn orange and iodine will turn purple. Now, if you had chloride ions dissolved in cyclohexane, then adding bromine to this solution would turn your solution orange. If you were to add chlorine, nothing would change. Similarly, if you had bromide dissolved in water, then adding chlorine or bromine will make no change. Now, adding iodine to either will cause it to turn purple or violet because iodine is the most reactive. Now you'll need to know the term disproportionation, and disproportionation is a reaction where both reduction and oxidation occur to the same element. As an example, you can see here that chlorine is both oxygenated and reduced because as an element it is 0, and then it is either +1 or -1 when it comes to the products. Now, this is a disproportionation reaction that you will have to memorize, and it is the formation of bleach. So you just have to sit down with this one and just know it. Now, chlorine can be used to create clean water. It does have some disadvantages though. Chlorine gas is very toxic, it can be an irritant or it can be fatal, and you have the chance to generate chlorohydrocarbons, which have been linked to cause cancer. Now, obviously these are bad, but it is much worse to drink unclean water with pathogens and things like that in it than it is to risk these. Now, another test for halogens is with silver nitrate, and as you can see here, it forms silver halide. But first we need to go over the polyatomic anions. So these are anion tests. They test for negative ions, as the name suggests. So first of all, we have the carbonate test. This is the carbonate ion, which you hopefully have memorized. So you add dilute nitric acid to whatever your carbonate is, and then you pass the gas that's produced through lime water, and then if the gas produced turns lime water cloudy or milky, then it's carbon dioxide. And if we're testing for a sulfate ion, then we need to add some sort of barium, and barium will react with the sulfate ion and create a white precipitate. Now, the barium compound you use depends on what test you're planning on doing next. Now, you can do barium chloride or you can do barium nitrate. I would recommend just memorizing barium nitrate because if you put it, you can't be wrong, but if you put barium chloride, you could be. Now, back to the silver test. Silver halides will make different color precipitates depending on the halide used. And you can see the colors here, and this is something you'll need to memorize. Now, white and cream can be very hard to distinguish, and you can use ammonia to help you with this. Now, dilute ammonia will help you distinguish chlorine from the others. And concentrated ammonia will help you distinguish iodine from all the others. Now, there is a specific sequence to these tests. You don't need to know the reason why, you just need to know the order. And the way I remember the order is with crash, which is carbonate, sulfate, and halide. Now, the only anion you need to know how to test for is ammonium. Now, if you add hydroxide ions to ammonium ions, you get ammonia and water, and this acts as a base, or because it's dissolved in water, as an alkali. If you heat it, the ammonia is given off as a gas, and that means you can use moist indicator paper, place it into the vapor or gas, and it should turn blue. because ammonia is basic. And now we need to learn about enthalpy. And enthalpy is the measure of an energy change within a reaction. Now, if a reaction is exothermic, this enthalpy value will be negative, and if it's endothermic, it will be positive. And you work it out through the enthalpy of the products minus the enthalpy of the reactants. So this is an enthalpy profile diagram, and you might need to draw one of these in your exams. So it's important to know what they look like. So this one here is exothermic, and you can see that because the delta H line goes downwards. Whereas this is endothermic because the change in energy is positive. Now, if you're paying attention, you might have noticed the activation energy is on there. That's not always necessary, it depends what the question asks you to do, but we represent it with EA. And this is a definition you'll need to know. So activation energy is the minimum amount of energy required for a reaction to take place. Now, before we do the next bit, you need to know what standard conditions are. Now, standard conditions are very simple: 100 kilopascals, 25 degrees Celsius. If there's any solutions, then they're expected to be 1 mole per decimeters cubed, and all products and reactants have to be in their standard state. The first definition you'll need to know is the standard enthalpy change of reaction. You can also write it like this: an enthalpy change that occurs with a reaction in the molar quantities shown. The next one is standard enthalpy of formation, and that's the enthalpy change that takes place when 1 mole of a compound is formed from its elements. This sometimes means that in certain equations you will have to do like half elements, but that's fine. Now the next one is the standard enthalpy change of combustion, and that's the enthalpy change that takes place when 1 mole of substance reacts completely with oxygen. And then you have the enthalpy change of neutralization, which is the enthalpy change when an acid or base is neutralized to form 1 mole of water. Now, if you're writing the definition in an exam, it's important that you keep this phrase at the back of your mind. Under standard conditions, with all reactants and products in their standard states, might be the difference in marks, so just make sure when you're writing the definition, you include that little phrase at the end. Now, before we do any maths, we just want to go over some simple unit conversions. To get from degrees Celsius to Kelvin, you add 273, but any change in Celsius is equal to change in Kelvin. Now, the calculation you'll need to know is that the change in energy is equal to the mass times the specific heat capacity times the change in temperature. Then if you take your energy and you divide it by 1,000, and then you divide it by your number of moles, it will give you your enthalpy. Now, for combustion, you can use something called a spirit burner, that you can measure the mass before and the mass after to work out the mass obviously used in the combustion. Problem being is they can be very inaccurate. There can be a loss to surroundings, incomplete combustion, evaporation from the wick, and obviously you can have non-standard conditions. And you can see here that the first 3 will make it less exothermic, non-standard conditions will make it more exothermic. Now, for the standard enthalpy change of reaction, you're going to use styrofoam cups because they offer some level of insulation, and you're going to measure the temperature change, and you're going to calculate the mass of your reactants using density. Now, you can see here an enthalpy diagram, temperature one side, time on the other, and you can use this to calculate the total change in energy. Obviously, if you're using a thermometer, there's going to be a delay between the readings and the actual peak in temperature. So what you want to do is you want to extrapolate your line, and you want to kind of go upwards from just before your temperature increases a lot, and then go across, and you can find your temperature at its peak. Now, the enthalpy change of neutralization, you'd work out exactly the same as you did last time, except you're using 2 solutions, so you have to use 2 densities rather than a density and a mass. So we also have bond enthalpy, and that's the energy required to break 1 mole of a specific bond. And this is always positive, and it's also an average because realistically the value depends on other bonds nearby. So if bond breaking is endothermic, it makes sense that bond making is exothermic. So if you make more bonds than you break, the reaction is exothermic, and vice versa. Now, in an exothermic reaction, you can break bonds and then you make them, and so your total is exothermic, as you can see from this diagram. And you can use this sort of diagram to look at something called Hess's law, which works out enthalpy indirectly using the conservation of energy. Now, Hess's law is nice and simple. If C is too difficult to measure the enthalpy on accurately, you can go from your reactants through route A and then down route B to get to your products. Now, the rate of reaction is equal to the changing concentration over time, and it has these units here. Now, the rate is highest at the beginning because all the reactants are at their highest concentration and so react with each other more. And there are many ways you can increase the rate. You can increase the concentration, increase the temperature, introduce a catalyst, or increase your surface area. And these work because of something called collision theory. For a reaction to take place, two particles need to collide successfully and form a product. But these successful collisions require the correct orientation and sufficient energy. If you increase concentration, there are more particles in the same amount of space, so there's a higher chance of more successful collisions, and the exact same is true for pressure, it's just gas. And you can measure the effect of concentration through two methods: the removal of a reactant or the production of a product. So in a reaction where a gas is produced, you can either measure the volume of that gas produced or the mass lost. So what about catalysts? How do they help in a reaction? So you'll remember activation energy from earlier, and all a catalyst does is lower this activation energy by providing an alternate reaction pathway. Now, there are two types of catalysts: homogeneous, which is same state, and heterogeneous, which is different state. Now, a homogeneous catalyst will form an intermediate that then breaks down to regenerate the catalyst, whereas heterogeneous catalysts are absorbed and then desorbed. Now, catalysts are really important in industry because they reduce the amount of energy needed, and that reduces costs, obviously, and it also reduces the amount of CO2 produced. So next we need to look at Boltzmann distribution diagrams, which you can see here. There are two things you need to know for Boltzmann distribution, and that is number of molecules and energy are the two axes. And because there are no molecules with zero energy, it meets the origin, but then it does not meet the x-axis again, because no matter how high your energy, you'll always have at least one molecule with that energy, except for infinity. Now, the area underneath the Boltzmann distribution diagram is equal to the total number of molecules in the reaction. And so past the activation energy line is the number of molecules that can react successfully. Now, if you increase the temperature, you increase the amount of molecules with activation energy or more, which is why the red line is higher at the activation energy. Now, the peak in the first temperature doesn't exist as much in the second temperature, and that's because you want to keep the area the same, because you're not introducing new molecules into the reaction, you're just changing the temperature. Now, introducing a catalyst doesn't change the amount of molecules with an activation energy. Instead, it lowers the activation energy. You can see here I've drawn it with the symbol EC. So the area is larger, so there are more molecules with that lowered activation energy. Now, this symbol here means a reversible reaction, an example of which is on screen now. Now, where you'll have a reversible reaction, you'll also have an equilibrium, where the rate of the forward reaction is equal to the rate of the reverse. Now, it's important to know that at this point, concentration doesn't change, and we are working within a closed system. And that gives us something called Le Chatelier's principle, which you'll need to know the definition of, which states that any external change to equilibrium means the system will readjust itself to minimize that change. And this concept can be investigated with colored reactants or products. In this example here, at equilibrium it would be somewhere between yellow and orange, and if it would shifted right, then it would be more orange than yellow, and likewise if it had shifted left, it would be more yellow than orange. And this one's a slightly better example because pink and blue are more easy to distinguish than yellow and orange. Now it's important to note that catalysts don't change the position of equilibrium. Instead, it's things like temperature, concentration, and pressure that do. Increasing concentration favours the side with the most moles of reactant or product. Increasing temperature favours the endothermic reaction, but catalysts don't change equilibrium at all. And now we need to work out something called the equilibrium constant, and you work that out as you can see here. Now when writing the expression for this, you always want to use square brackets, because square brackets is chemical shorthand for concentration of. Now the equilibrium constant indicates the proportion of reactants to products, and so its value can help us guess at where the equilibrium is. Now if the equilibrium constant is equal to about 1, you can guess that the equilibrium position is about halfway. If it's greater than 1, you can guess that the equilibrium shifted towards the products, and if it's less than 1, you can guess that it's shifted towards the reactants. And that's it, that's module 3 done. Thank you so much for watching. I hope it helped in some way. Remember to like and subscribe, and I'll see you for module 4. Bye!